Hello and welcome to MATLAB programming for numerical computations. So what we have done in all these lectures so far is solve various problems using MATLAB scripts. However, if you want to develop a generic solution technique that you can then reuse for different problems, it actually makes sense to have a MATLAB function in order to do that. An example that we covered in module 3 was the trapz function to calculate integral using trapezoidal rule. So if we want to create a function of the same sort for solving linear equations, that is something that I'm going to talk about in today's lecture. We can call this as a lecture 4.4a. Okay, so let's go on to MATLAB and open our previous file, Gauss Seidel. Okay, and now what we want to do is, rather than having this as a script file, we want to have this as a function file. What it means by having this as a function file is our A and B matrices are going to be supplied to us from an external calling entity, and we are going to solve this and return our solution using this. Okay, so we will say function uh, x equal to Gauss Seidel a comma b. Okay, and we'll have to delete these. I will just cut these. I'll go on over here and I'll just paste them over here so that we have A and B in our workspace. Okay, sorry. Okay, so now we will put the comments after the function. So solving AX equal to B using Gauss Seidel, and that's pretty much all that is needed. With respect to initializing, let's move this n at right at the top, and n is going to be nothing but length of a. Okay. Usually when you write functions of this sort, you also need to do certain error checkings. For example, we want to check that A is an n by n square matrix. We also would like to check whether B is an n-dimensional vector. I'll skip these steps for now. Okay. And so we will just go ahead and do this. We will probably need to delete the diagonally dominant elements, and we will just call this as AS, and that should be good enough. With respect to initialization, the X is indeed initialized in this way, and max error is initialized in this way. We would also like to have this 25 as another variable called max iterations equal to, let's say, 100. Okay, so once to max iterations, and we will also need a tolerance tol x equal to 1.0 e minus 4. Okay, so this is what we need. And so what we have done so far, is this: the things that we had hard coded. For example, we need to do this for 25 iterations. We have now kind of given a variable which is called max iterations. When do we tell our solution methodology to stop? Rather than deciding that in an ad hoc way, we are trying to formalize that using the tolerance, which we call as tol x. Okay, so, and we don't want our code to keep displaying these results, so instead what we need to do is if max err is less than tol x. So what we mean by that is the maximum of the error is less than tol x, then we want to break. And what break does is it breaks from the for loop, which means that it's going to come out of the iteration for loop. Before we do that, we would also want to give is solution equal to true. Okay, and we will say is solution equal to false here. Okay, so that's a flag that basically tracks whether or not the solution is converged. So if the solution is converged, I'm gonna say that is solution equal to true. Otherwise, it returns is solution as false. And this is something that we want to return as well. So x comma is solution. Okay, so this is what we have so far, and yeah, so we will save this. And now what we need to do is basically call this function using our usual function calls. So Gauss Seidel a comma b. Okay, and if we just give this as Gauss Seidel a comma b, the first output argument will be returned as the a and s. That's the array, that's the vector that captures the solution. Okay, and if we use this Gauss Seidel a comma b in a naive way, what we are going to get is basically an incorrect solution over here. And the reason we do get that is because this overall matrix was not diagonally dominant. Okay, so let us consider the more diagonally dominant case where basically we have replaced the first and second rows that should be sufficient for us for our purpose. So we can say a uh, a new 1 comma all equal to a 2 comma all a new 2 comma all is going to be equal to a 3 comma all, and a new 3 comma all is gonna be equal to a 1 comma all. Okay, and same thing with b new also. So b new 1 is going to be equal to b2. B new 2 is going to be equal to B3, and B new 3 is going to be equal to B1. Okay, or actually I should say B1 comma 1, B2 comma 1, and B new 3 comma 1. Okay, and we press enter and we see B new is this guy and A new is again rearranged matrix. Okay, so now we call Gauss Seidel using A new and B new, and we get the solution using the Gauss Seidel method, the solution that we stop when the tolerance of 10 to the power minus 4 is met. Okay, so if we want to look at our flag as well, we can write this as x comma I flag equal to Gauss Seidel a comma b, and the flag should say that it's not converged. So the flag is 0. Flag is 0 means that flag is false. That means is converged, so is a false state. And if I repeat that with a new, b new, okay, I'm gonna get flag equal to true, which means that the solution has converged within the desired tolerance value. Okay, and our solution is captured in the vector x. Okay, so what we have done over here is took the solution of the previous problem that we did in lecture 4.4 and converted it from a MATLAB script into a MATLAB function which we now hope to use later on for various other computations if desired. Okay, so this is how you would build your functions and your files in order to build a large set of programs as you become more and more experts in MATLAB. So with that, I come to the end of lecture 4.4a, and next lecture we are going to talk about an exciting new method called Thomas algorithm or tridiagonal matrix algorithm. Thank you and see you in the next lecture.